Okay. So good afternoon, everyone. Sorry about that. Thank you for joining us today for the live webinar on carbon, humic acid, and soil health. Before we get started, I just want to extend a big thank you to the Andersons for putting on this webinar. I'm Alex Retsky, Digital Media Project Specialist for Annex Business Media, and I'll be your moderator for this session. Before I pass it over to your speaker this morning, I'd just like to take a moment to go over a few housekeeping items. Firstly, this webinar is being recorded, so for any reason you have to leave early or you miss any part of the presentation, a link to the recording will be sent to all registrants shortly. Secondly, the audience is in listen-only mode, so cameras and microphones will be turned off for you. However, the Q&A section and the chat section will be open, and we will have a Q&A section at the end where all questions will be answered. Now I'd like to introduce your speaker for today. Ben Pease, PhD, is the Turfgrass Agronomist for the Andersons. He earned his undergraduate and master's degrees in soil science and horticulture at the University of Wisconsin, focused on turfgrass management, and a PhD in horticulture from Iowa State University with a focus on turfgrass science and physiology. Thank you, Ben, for being here. I'd like to pass it over to you for your presentation.
All right. Well, thanks for everyone for viewing in here, and thanks to Turf and Rec for helping us put this on. So yes, I'm the Turfgrass Agronomist for the Andersons. If you're not familiar with the Andersons, we are based out of Maumee, Ohio, just an hour-ish south of Detroit. We do distribute all across Canada, North America, and even international beyond that. So as a turfgrass agronomist, I'm in charge of educational outreach events like this and product research and development. We also do a lot of in-house research as part of ongoing product quality and developing new products. So many different hats. This is one of them today, and our topic today is carbon, humic acid, and their interaction and how they interact and influence soil health. So let's look at an agenda. We will start off with the importance of carbon in relation to soils and what it does for plants. We've got humic acid and soil health, how those interact. And then we've also got, we're going to go through the why and the how of humics. So what are humics doing to our turfgrass systems on a plant level basis or a soil level basis? And we'll look at some humic product research that's been done over the years by the Andersons and by other individuals as well. And we'll talk a little bit about how to use humic products in a turfgrass fertility program, how to use, when to use them, maybe how to, when to apply them, which type of applications to do. Get into a little bit of that towards the end, but a lot of how you use them is up to yourselves. 1 second, let me silence something back here. Okay, moving forward. Sorry about that. Let's start off with the importance of carbon. So we know carbon is the kind of the keystone for a lot of things in the plant world, the soil world. Really has a lot to do with all of our soil processes. This would be the physical, chemical, or biological processes. Physical, just the makeup, the structure of soil. Chemical, how nutrients and ions are interacting in the soil. And biological, of course, it's that refers to anything microbial or living within the soil system. So all these parts of the soil profile do rely on carbon to some extent or another, and then therefore our plants do as well. Much like a nutrient, if we don't manage our carbon levels within the soil, we can find that carbon limits the growth and the quality of our plants, of our turf. So just like we could have a shortage on nitrogen, phosphorus, potassium, other nutrients, micronutrients, we can have a shortage of carbon. And if we're not feeding the soil system with enough carbon, as if we're taking it away through clippings or erosion, things of that nature, if we're not replacing that carbon element, then we could be deficient and have issues. So looking at carbon in relation to humics, we look first kind of at soil organic matter. And this was kind of a light bulb moment back in my turfgrass soil science days. You know, we only need 3 to 5% to have a very productive soil, 3 to 5% soil organic matter. So small number, big effect. So doesn't take much to do a lot with when it comes to organic matter and carbon, but you do need some. So of that soil organic matter, so we're thinking just 3 to 5% of the overall soil volume, soil bulk. 60–80% of soil organic matter is what we generally call humic substances. And some people will call them humic materials. There's a few different terminologies out there in the literature, but 60–80% of the 3 to 5%. So now we're talking just 1 to 2% of our soil organic, our total soil volume is humics. And then we break humic substances down into a few different categories, as you see here. So we've got fulvic acids, humic acids, and humins with an I. So if we look at those few categories, those categories are important because they're going to do different things within the soil system and different things for our plants. Fulvic acids, we'll start with these because these ones are highly soluble, but they do contain the most effective carbon-containing chelating compounds. And by effective, I mean kind of the most available, the ones that are available the quickest, the most available to the plant system. Humans, on the other hand, these are not water soluble. So if you've got a liquid humic acid product, it's not a humin, it's maybe a fulvic. So humans, while they're not water soluble, they are effective in the soil system. We need them for water holding capacity, to soil structure improvements, soil stability. A lot of cation exchange capacity is occurring in these these human portion of humic substances. So while they're not soluble or readily available, they are important. And then finally, when we're looking at turfgrass specifically and a lot of turfgrass fertilizers or turfgrass products, you're usually thinking humic acids. So these are more soluble than humin, less soluble than fulvic, kind of right in the middle. They're more reactive in the soil than humans as well, so they're more available to the plant. But as far as the plant's concerned, they're very important for ion exchange, chelation of nutrients within the soil system. Chelation, then therefore meaning, ion or nutrient availability. So looking through the literature, through the research that's been done over the years, on turfgrass and then a long list of other crops as well, we see a pretty good trend revealing itself that there's some big benefits to using humic acid as part of a fertility program. So going back to the first part of the hour, if we're applying humic acid, we're addressing our soil carbon levels, our soil carbon bank, because humic acid is a really good source of carbon. So we're adding carbon to the system, providing microbes a place to live. Microbes are feeding on these carbon food sources. If we have happy, healthy fed microbes, our soil is very healthy. So we're promoting good soil health, good plant health. Humic acids have also been shown to improve soil structure. So looking back to the other slide when we were talking about humans, they're improving our aggregate stability, improving water infiltration and holding capacity. If we have these humic structures, humic substances within our soil system, we then have better soil aeration as well. So aeration meaning we have a good balance between water, air in the soil voids, but then we also have enough soil colloids to have a good soil structure. So we can't have no aeration, no water in the soil, have this very compacted soil, though that doesn't do us any good. But if we're constantly or routinely getting more carbon into our system, soil system, then we're going to help save soil structure or keep a good soil structure. Humic acids, when we look at the plant specifically, do tend to change root structure drastically. So we're plants that are fed with fertilizer plus humic usually have increased root mass, increased root density, and functionality. And by functionality, I mean root hairs. So where actually a lot of the exchanges are occurring, root hairs, root branching. We're having much more effective roots that can better mine the soil, for lack of a better term. If you've got much more root surface area and root hairs, you're going to get better nutrient uptake and water uptake. So improving root structure is a big thing as far as the benefits of humic acid. Soil health, so that's a term that's really kind of come around in the last 5 to 10 years in the turf world. So maybe we're a little late to the party. I know it's been talked about in row crop agriculture for a long time, but it's a good topic and an important one. So when we talk about soil health, we're thinking about nutrient levels. So what's the cation exchange capacity of that soil? Is it able to hold nutrients that we're applying? Can it hold water? Can it hold the rainwater or irrigation water that we're providing? You've heard me talk about soil structure. Soil structure is very important for plant health. It's also important for soil health. So if we have a really compacted soil that's just not getting aerated or water into it, that's an unhealthy soil. So we need good soil structure. If we've got good structure, our leaching can be reduced, runoff is reduced, plant or microbe life is improved because there's food sources, there's water sources, living sources in a healthy soil. And then with the talks now of potentially selling carbon credits, we want to make sure we're maybe capturing all the carbon we can. And there's no better system out there than a turfgrass system to capture carbon and then store it in the soil. So all those roots that senesce and die off, that's putting carbon back into the soil. But we can also do it through fertilizers that contain a humic acid or just a strictly standalone humic acid application. So if we think about all these factors together, if we've got healthy soil, we're more likely going to have healthy turf, because all these factors feed into, can the plant get the water and the nutrients that it needs to keep the quality, color, playability, what have you, of a good turfgrass system. So a little more on soil health, and you can kind of see a theme here on how the attributes of a humic acid or attributes of a carbon application play into all these factors. So if we look at soil health, we really measure 3 different buckets or categories. We've got our physical, so texture, porosity, density, aggregate composition. These are a lot of the things that you can maybe see, feel, measure, things that might be on a soil test report. So think of it in that regard. Biological, we've touched a little bit on microbial activity, how much microbes are in the soil. What are they doing? Are they mineralizing nutrients that are there? So are they making them available for the plant? There's a lot of nutrients in the soil are stuck on soil colloids, and we need these microbes to, air quotes here, release them so that the turf can use them. Respiration is an activity of microbial populations, enzyme activity, a lot of biological factors. So again, this bucket, anything kind of living, moving in the soil system. And then we've got some other measurables. We've got chemical. So organic matter is a big portion of this. What's our percentage of organic matter? So we go back to what we were talking about earlier, that 3 to 5%. does a lot of the heavy lifting here in our turfgrass soil systems. So some of this will be on a soil test report too. These are measurable. pH, cation exchange capacity, what are your nutrient levels? You know, these are pretty familiar from a soil test report. They'll show you, here's your NP and K and your micros. Maybe you need to add such and such to get it at a different level. So all things to watch for in soil health, but they play into our thinking of carbon applications, our thinking of humic acid applications to build this healthy soil. Okay, so moving into a little bit of the how of humics. So what are these things doing within the soil? How are they actually improving our plant or our turf quality, color, things of that nature? The visuals that I like to start with here on the left is a soil textural triangle. So if you know how to read this, you can figure out from a soil test, you know, if it measures your aggregates, it'll tell you percent clay, percent silt, percent sand, and you trisect all those, you know, depending on what percentage they are, and you know what type of soil you have. So whether you have clay, silt loam, sandy loam, that'll tell. Just knowing that's going to tell you a lot about, well, do we really need to add humics or carbon? You know, if it's a clay, sandy, clay soil, sandy soil, the answer is usually probably yes. You know, silt loam, those are much more robust soils that don't often as times need as many amendments. So this is always something to keep in the background. But the biggest thing that that we measure, or that, the research has shown, is that humics help improve nutrient availability. So looking at your classic nutrient availability chart by pH, so the one on the right, we see that there's areas that turn yellow and turn red. So that's depending on the pH, each nutrient has a different reaction with soil pH. And you can see some become relatively unavailable quickly. So phosphorus has a very small band of green in the middle. Same with calcium. If we get outside of 6.5 to 7.5, phosphorus and calcium can become unavailable. So that's without humic acid, we see a very small range here on the left where your soil needs to be in 6.5 to 7 to get most of your nutrients. With humic acid, and obviously this is, we're a little bit of an exaggeration. We take all of the blinders off, but we'll show shortly here how humic acid is able to keep these nutrients available across larger pH ranges. So that's the basics of how humics help improve nutrient availability. So with humic acids in the system, we can see that humic acids assist with micronutrient uptake. So they'll activate a lot of these proton pump channels that help get nutrients into the plant system. So we're trying to move plant nutrients from a low concentration in the soil solution to a high concentration in the plant. And humics help with that uptake, that uphill uptake, moving from low concentration to high. That does take energy and take initiative. So they assist with micronutrient uptake. They also help readily assimilate carbon for soil microbes. So if we keep these soil microbes fed and healthy, these soil microbes will then release or make more nutrients available towards plants. So it's feeding from both directions. We're making these nutrients available on their own just through humics, but then the humics are feeding the carbon feeds the microbes, and the microbes therefore mineralize or release more nutrients within the soil. And we also see humic acids increasing sugar organic acid content. Now that may sound a little daunting, but what that does is help change the rhizosphere, help root exudates, increase root exudates so that roots are able to grow through the soil better, and we'll see some root rhizosphere acidification info in a bit. So nutrient uptake is a big thing. I briefly mentioned changes to root architecture earlier, so here's some visualizations of that. So when we treat this plant with humics, we've got our control here, and then we've got a humic acid treated root system on the left. So looking between those two, just the overall biomass increase is there. 3 to 4 times the biomass. Root branching is very important. Root hair increase. Root hairs are where most of the interactions are the surface area of those root hairs is so immense compared to the actual root itself that's where a lot of the interactions are occurring. So more root hairs, more surface area, more lateral roots, we get more branching. Rhizosphere acidification is a big one. So these root exudates, that's what, the root tip is exuding these exudates. It's almost kind of a lubrication for the root to go through the soil. But what these exudates also do is they acidify the rhizosphere. So rhizosphere is the area directly around the root hair, the root area. And if most of the time we're in higher pH soils, it will acidify just enough of that soil. I mean, just the interface between the soil and the root hair, where now we can bring that pH of the rhizosphere down just enough so that more nutrients are available. So small changes in pH in a small area of the soil can make a big difference. And that's all related to root architecture. And so that feeds back to the last slide where we talked about nutrient uptake. So if we're getting root rhizosphere acidification, we're getting increased root hairs, increased root branching, we're going to get better nutrient uptake. So that's how humics are working behind the scenes to move more nutrients into the plant, make nutrients more available to the plant. Now, some interesting things happen, inside the plant as well. So if you think of a cell membrane, we're trying to get nutrients from low concentration over here to high concentration over here to get it into the plant and move it throughout the plant. So even within the plant, we've got some nutrient gradients that we have to tackle. And a way that is done is through proton pumps, and proton pumps take hydrogen, take the H plus ions, trade them across, and they take enzymes. One of them is ATPase. So it's a major enzyme that helps move items across the plasma membrane. So that's just from one cell to another. And what humics do is they activate these pathways or activate these pumps. And so that can all feed back into the plant now being better able to drive mass flow, to drive nutrients to these pumps. So we're increasing our root mineral nutrient uptake by harnessing these channels, activating these pathways, and moving nutrients into and throughout the plant. Interestingly enough, this H plus ATPase also initiates cell wall loosening. And so if we're getting cell walls that are more elastic, especially in the root area, we can now grow longer, more numerous cells in the root system. So that's where we're seeing the changes in the architecture, more branching and overall length and mass, because we've loosened. It allows cell walls to grow, expand on a more elastic basis and just grow a little easier. Interestingly enough, these processes also add to the plant being more adaptable to stresses. So any abiotic stresses that occur, drought stress, temperature stress, the plant is better adapted because they've got better they're better fed. They're not expending as much energy to directly uptake nutrients. They've got humics to help out. So stress adaptation is a big portion as well here. Alex, I've lost I don't see myself anymore. Are we still okay?
Yep, everything's looking good.
All right. Said something changed over here that, well, I better just check in. All right. And lastly, we already touched on the acidification of the rhizosphere. Again, these pathways help the root structures, the root architecture improve and expand. Next up, we want to talk about nitrogen use efficiency. So humics have a role in this as well. So if you think about nitrogen in the soil system, you can see it kind of disappearing and reappearing there. We do lose some nitrogen through leaching or through gaseous emissions. So think back to the carbon cycle. I'm sorry, the carbon cycle, sorry, the nitrogen cycle. We can lose it going through the soil system through that's leaching. It can volatilize. We can lose it into the soil system itself and not be available. Humics help stop leaching by increasing the soil organic matter, and so there's places for the nutrients to go rather than just running through the system. So we did touch on that humic acid improves root development, cation exchange capacity, stabilization of soil aggregates. So this is where we're giving places for nutrients to be held, be stored, rather than being lost through leaching or volatilization. So we see improved nitrogen efficiency, minimized leaching. So we're increasing our nitrogen use efficiency. So the nitrogen that we are applying is getting better, is being used more efficiently. This also plays out on the phosphorus side. So we know that at certain pHs, phosphorus gets tied up in the soil, or certain soil types really, the phosphorus adsorbs onto the soil. It gets held in the soil. It's there, but the plant can't access it. So we do also know that phosphorus in the soil solution is often a lower value. You know, many times we've gotten away from phosphorus fertilizers due to certain environmental conditions. So we're already dealing with a limited supply. And we know that once we do add phosphorus, many forms of phosphorus are short-lived. They're available quickly, and then they get kind of taken over by the soil system, depending on the pH. So you can see this graph here. And if you think back to the graph or the figure with all those different lines of all the nutrients, we really see our best phosphorus availability right around neutral, 6.5 to 7.5, somewhere in that area. Outside of that one little spot, phosphorus is getting bound to items in the soil, and it's not plant available. So humics work to keep the phosphorus plant available, and they form what's called these aluminum or iron. You can see aluminum or iron here. This humic metal oxide complex, and that uses, like I said, aluminum or iron. Here's our humic acid particle, or kind of component in the soil system. We've got aluminum and iron that now holds this phosphorus. Rather than the phosphorus getting onto a soil colloid, it's attached to this humic aluminum or humic iron complex. So when we bind phosphorus to this, it is still plant available. If it's bound to the soil, it usually isn't plant available. So humic acids, even outside of that small pH range, will hold on to phosphorus and keep it available, keep it in a more available form than if it were bound to a soil colloid. So these aluminum or iron oxides help increase phosphorus availability when we have humics in the soil solution as well. So phosphorus doesn't leach, but it gets bound up, and this is how we can keep it available and increase its usage efficiency. All right. So we're going to move into the Humic research kind of summary here. So we'll go over a few trials. If you are interested in knowing, even further details of any of these or a bunch of other work, there is a Humic research trials guide on the website andersonspro.com that will have a lot more detail, a lot more numbers, and give you kind of the parameters under which these trials were conducted. So, like I said, one of the big claims of humic acid fertilizers or humic acid products is that they can potentially reduce your nitrogen usage. So, not replace it, but reduce it. So here's a trial showing this, done a few years back. We looked at Kentucky bluegrass. This was just 2 applications of fertilizers throughout the year. And you can see we've got a pretty well balanced 1608, and we've got 3 rates of that 1608. A 1 pound, so think of the normal rate, and we got a 3/4 rate and a half rate effectively. And then we're adding a humic acid product to the lesser nitrogen rates. And summarizing these 2 years on the left here, the untreated is the gray one at the bottom. The yellow line is our full nitrogen rate, so 1 pound per thousand, and the 2 green ones are then the reduced rates. So interestingly enough, especially in the second year, first year, okay, maybe we're just riding out some nitrogen that's in the soil. But if we get into the second year and we're in year 2 of reducing our nitrogen rates, and we're still getting similar quality to the control, the positive control of 1 pound nitrogen per thousand, you can see these are all bundled right at the end after 2 years. We still have the same level of quality, even though we've reduced our nitrogen rate by almost 50%. That lighter green line is almost a 50% reduction. So we can employ lesser amounts of fertility, but still keep the color, quality, playability, performance that we've always had. Expanding on on that, this was the same, a different location a few years later, same idea. We've got Kentucky bluegrass at 3 inches. Now we've got a few different products. We've got a polymer coated humic fertilizer. We've got just standard urea. These are both at full rates. Then we've got reduced nitrogen rates with urea and the polymer coated one, but then adding in more humics to the system. And this trial took it to another level. Instead of just 2 applications per year, we made 4. So more of a standard fertility program. Not many people are only doing just 2 applications. So let's take it to the next level, put out 4 applications and see what happens. So urea full rate, let's look at that. Here it's this lighter gray line. And you can see in both years, you almost don't notice it because it's stuck behind all of the other treatments. Now, yes, we do have a full rate of our polymer coated, humic coated fertilizer, and that's the darker green. But again, all of these ones are kind of bunched up. Even by the end of year 2, of course, the half rate maybe is a little less than ideal, but our 3/4 rate of urea plus a humic product is right there with the full urea rate and the full rate of another urea fertilizer. So 4 applications a year, we can safely reduce our nitrogen rate by 25% and statistically not lose any quality. We're looking at a quality of 8 versus like a quality of 8.2. Something that the end user's eye couldn't tell the difference between. So again, same level of quality achieved with less nitrogen when we've added a humic product to our fertility program. Okay, another example. So you're probably thinking, well, Ben, that's great. 3-inch height cut of turf. What about my golf greens, my fairways or tees? So again, we took it to the next level here and did this on creeping bent grass, mowed at 1/3 of a centimeter. We're doing, excuse me, 0.15 pounds of nitrogen every other week, April through October. So kind of the Midwest growing calendar. And we'll set this up so we have a full nitrogen rate here. So we'll just call that 1 pound per thousand. And that's with the humic urea. We now have got that same humic urea at a 2/3 rate. And then we've got our urea at full rate. So we'll say 1 pound per thousand. And then non-treated control. So gray bars are year number 1, green bars are year number 2. So you can see our control is consistently about 5.5. But then all of our treatments are in the high 6s, low 7s. So without fertility, this would be an unacceptable putting green, because 6 and above is kind of where you cut it off as acceptable. But the real thing to think about here is that you see asterisks in each of these column groupings. So between the 2 years, there's no statistical difference. So year 1, year 2, and between each one of these, if you look at all the gray bars and all the green bars, there's no statistical difference between any of them. That means this 2/3 rate performed just as well as both of the full rates. And that's the case even in year number 2. So we went through 2 years of reduced nitrogen, and we don't see a reduction in turfgrass color or quality. So it does work on a golf course scale as well, golf turf greens, even on a sand-based. All right, shifting gears a little bit in the research side. Now we're looking at using humics on a golf course. This is a golf course that had soil salinity problems. So I'm pretty sure they were irrigating with reclaimed water. And even with all the treatments you do to reclaim water, there's still going to be salts left. So these fairways were starting to have salinity problems, meaning they have high levels of salts. So they looked at this, well, what can we do what happens when there's high levels of salts? That's sodium. Sodium is a large ion. It pushes off all of the other nutrients off of the soil colloids. So the soil loses structure, first off. Second off, it's losing its cation exchange capacity. So now we're having a turf that's hungry, and the turf that's now growing on a soil substrate that's not healthy. So there's 2 things working against this turfgrass system. So what they did here is we're going to top dress these fairways with various amendments to see if we can combat this salinity problem. So they did sand, sand by itself. We have sand plus peat at 90 to 10, and then an 80-20 version. Well, then how about no sand, but just humic acid? And I believe this was a liquid product. So they were spraying this and then watering it in at a rate of 1 gallon or 3 gallons per acre. So looking at just 1 year of this trial, visual quality, again, anything 6 or higher is acceptable. So even in the early part of the year, the only treatment that was acceptable was the high rate humic acid. And you can see that the high rate humic acid throughout the first 4 months had the highest rated. Only in September did the sand plus peat overcome it, but if you look at the A's, these 2 are statistically similar. So 8.1 and 8.2 are statistically the same thing. While 8.2 is a higher number, they are the same mathematically. So earlier in the season, we're getting better quality with humic acid, and that better quality continues out throughout the rest of the growing season. Now, any amendment with peat or humic did well. So I've circled these because they are different than the control. So the letters behind the control C means anything without a C is better than the control, and then so on and so forth, D here and C here. So the circled ones are the ones that are better than the control if you did nothing. So we've got the biggest differences from the control being the high rate of humic, or secondarily, the low rate of humic or the sand plus peat option. So peat has humic in it. So we're not outwardly saying a humic acid application, but there's a lot of humification going on with peat products. So anything with humic, you can see increased turfgrass quality throughout most of the year. So really what's happening here is these humic products are helping the soil microbial biomass, helping restore cation exchange capacity, helping knock off the sodium from the soil colloids so that we can improve cation exchange capacity, improve nutrient availability, and then improve turf quality. So if you got salinity issues, peat applications or humic acid applications are probably a ticket to alleviating those issues. So thatch management is also a topic in regards to humics. There's some discussions out there that if you apply humics, you can reduce your thatch levels or at least keep them in check. So here's a trial that looked at the effect of turfgrass thatch on water infiltration rates. So the issue here is if we've got too much thatch, we're not going to get very good initial infiltration. So any small irrigation schedulings, that water is just going to sit up in the thatch layer. We'd have to have a lot of irrigation to fully soak the thatch layer, and then the water will go towards the rest of the soil system. This is especially prevalent on sand. We're basically creating somewhat of a perched water table with too much thatch. Once you can get through that thatch layer and get a constant flow rate, then there's no differences, but humics are helping break down this thatch layer to improve your soil infiltration, improve your water water infiltration. So water infiltration can be reduced through too much thatch, but if we look at some trials that involve humics and thatch management, we see some big differences. So here's a humic product, was applied for 2 years, both in the spring and the fall. You got two different rates. So we've got a low and a high, 150 pounds per acre, 300 pounds per acre. So not all that much if we're thinking on a bags per acre, we're thinking 3 bags to 6 bags per acre on a turfgrass scale. But if we look at this, what the graph is showing us is thickness on the y-axis. So I'll read these for you. That's roughly the thatch layer after 2 years, 2 applications per year is about 0.3 to 0.4 inches for both rates of humic, and the untreated is 50% higher at 0.6. So we see about a 50% reduction in thatch with a humic acid product application. So that's why I mentioned the previous one where we're looking at thatch and water infiltration. Well, if you do have a thatch problem that you're trying to alleviate, of course, aeration and top dressing, all the common cultivation practices are good to employ as well. But in addition, you can do a simple granular or liquid humic acid application once or twice a year, and use that tool also to help the other cultivation tools to get your thatch levels back to a manageable amount. So big reduction in thatch with even just a low rate of humic per acre. So looking at some ways to utilize humics, thinking about the research trials that we've shown and thinking about all the soil health factors that we've talked about, depending on what your goal is, you might be looking at a humic only product application. So there are various products out there that aren't tied to fertility. They're just a humic acid soil amendment type application. These are usually done on a granular basis, but there are some fulvic acid versions out there that you can mix into a tank and spray. And the better ones don't clog filters or nozzles, so be mindful of that. But these humic only applications do work good once or twice in the spring, once or twice in the fall. The only note here is just don't go too early because you do want the soil temperatures to be high enough where the microbes are going to be active. So think about that. It's similar to when you'd be thinking about pre-emerge, well, you're watching your soil temperatures. Watch your soil temperatures similar in a similar fashion when you're thinking about when to time your humic acid applications. And of course, I've hinted out at that there are humics that you can do as part of a fertilizer blend. So whether it's a homogeneous fertilizer or a blended fertilizer, there are many options out there that will put humic acid in as a granular filler. So instead of using limestone, we're using some sort of humic product, or we're covering the nutrients in a humic coating. And thinking back to those first few slides, you don't need a high percentage of humic to make things work. So in some cases, there's fertilizers where there's, it's such a small percentage of humic that there might not even be claimed. But in percentages in the realm, single digit percentages are still very useful as far as the humic componentry of a fertilizer product or the percent in the fertilizer bag. When it's part of a fertilizer blend tied to some nutrient applications, just a few percentage points moves the needle enough. So you could even do this on a spoon feeding basis where you're putting out, a tenth or 2/10 or a quarter pound of nitrogen in each application. You're spoon feeding a little bit of humic with those as well. If you have other soil amendment applications already on your calendar, thinking, well, if I'm going to put out gypsum or lime or any sort of biochar, there's combination products out there too, where those are all, two of those are not all, but two of those are combined to have humic plus gypsum or humic and biochar. And you can do two things at once with the combination product. If you're already looking to, schedule a different soil amendment application. So a lot of ways to use humic, and granular, if it's a granular application, you're usually thinking humins or humic acid. If it's a liquid application, you're looking more towards fulvic acids, and then some humics are also soluble. Well, we're getting close to the end of our time here today, so I want to show you some resources. If you're ever on our website, andersonspro.com, there's a lot of good educational items on there. Of course, the product listings are there too, but a lot of good background knowledge, and that's where you'll find the Humic Trial Research Guide as well. Now, the map there is only showing the US, but Ed in the green area, he goes into the western four Canada provinces. And the other sales reps then also go into we've got a sales rep, Dave Ruman, goes into the Eastern Canada provinces. Excuse me. So we've got some good resources for you, and reach out if you need their information. And then, of course, product catalogs specific to Canada. With that, I thank you very much for your time and attention. I know everybody's schedules are quite busy these days, so appreciate you taking time out of your day to spend with us. There's my name and contact information if you want to get a hold of me. And I think we've got some time for some questions if anything came up in the chat.
That's
Um,
awesome. Thanks so much.
please,
Oh, sorry.
oh, yeah, go ahead.
I was just gonna say I'm gonna leave my camera off just because I have had some connection issues today. If I drop off, I'll be back. It usually takes about a minute or two to reconnect, but let's get to
Okay.
some questions. The first one came about halfway through your presentation, and it's related to the presentation. The participant is asking, the issue is this is just straight nitrogen. What is the slow release amount in that blend? I don't know if you know what area he's referring to here.
Maybe some of the research slides, I
That's
would
when I
guess.
think it, yeah, I think that's when it came through.
Okay, yes, so one of those examples was using a 1608 fertilizer, I believe. And that one's a 25% slow release. So not overly slow release. Um, 15 above, I start thinking, well, that's a lot of soil release, but 25% is pretty standard. Now, the other one had a 40-0-0, and that was comparing 40-0-0 to, I think, urea and urea with humic, so on and so forth. The 40-0-0 is 100% slow release product. So that does have some benefits there, but it also had humic as a component. So even if we look at, let's say, a 50 to 100% slow release product, we do get, I'm sorry, let me flip that. 0 to 50% slow release product, we get a couple additional weeks of activity if there's a humic involved. So even looking at straight urea, the release for straight urea obviously is fairly quick. It's on even granular, it's on a level of 2 to 3 weeks probably. If you add a humic component, we seem to get another additional week out of that application. So the humic is, while yes, the slow release component of a fertilizer does have a lot to do with, getting continued quality. The humic does just add on another bit of time keeping nutrients available.
Awesome. Thank you, Ben. Got another one here asking, are there guidelines for peat soil on the website?
Oh, guidelines for peat soil. Not specifically on the website, but my initial reaction would be to take a look at your soil test. I mean, the organic matter is probably super high. So there are tests to figure out, the percent of humic in your soil already. So I'd be interested in seeing, what those might tell you. Might tell you that you're already kind of maxed out. There is a point of no return, loss of return on investment. So if your soil is already fairly healthy, then it's might not be something you see an effect of if you've already got a soil that's got good organic matter, good soil tilth, things of that nature.
Perfect. Thank you. Next one's a cost analysis question. They're asking, what is the cost analysis of this? So what was the cost of the 16, 0, 8, 25% versus adding in the humic?
Well, for better or worse, as the agronomist, I don't deal with cost much, but from what I gathered, looking at just, and these are going to be US numbers, your US dollar values. Like a standard 50-pound bag of urea is somewhere between $20 and $25. Now, if you have a humic coated urea, that bag is probably double that. So there is a price discrepancy there. Now, if you just are blending humic into a fertilizer blend, you might see and from what I'm gathering, an increase in cost of $1 to $3 per bag. And that'll be dependent on how much is going in, what fertilizer you're blending into. So yeah, there is an added cost, but the way to think about that is, well, I used to apply 1 pound per thousand of nitrogen. Well, now I'm only applying 3/4 of a pound. So you're probably gonna use the same analysis, but we're using 25% less of product. But yes, maybe the product cost me 5 to 15% more, but we're gonna use 25% less. So yes, they're more expensive, but oftentimes you end up using less of them because of that, because you're allowed to reduce your nitrogen rate because of all the humic activity. So again,
Oh,
I'm not in sales, I'm not in marketing, I'm just in the agronomist side. So that's the best I can do on a cost. The marketing people would probably have a different answer.
no, that's awesome. Thank you, Ben. I'm not seeing any other questions at the time. So is there anything you want to leave the attendees with on sort of like a final note before we wrap things up here?
Yeah, the biggest thing is if you don't measure it, you can't improve it. So if you haven't done some soil testing in a while and you're seeing some turf issues, it's always great to start with a soil test. There's most of the soil labs now will also do, you know, your standard one, but then there's also kind of a more robust version where it'll actually give you a soil health report. So measure a lot of different factors, bring them together and tell you what's the healthiness, air quotes, for what's the soil health level that you have. So that's a good place to start. They're a little more expensive, obviously, than your standard soil test, but if you employ that tool every couple of years, then you know your baseline, and you can start to see when you're getting to the levels where, hey, it might be time to do some sort of amending here or change our nutrient program. So soil testing is big when it comes to soil health and humic use, because in regards to that peat question, if you already have enough, well, you might not move the needle. So know what you have, and then plan from there. And always feel free to reach out to myself or anyone at the Andersons to help you interpret a soil test or decide, what might be the best course of action.
Perfect. That's awesome. Thanks a
Yeah,
lot. Really
you bet.
appreciate it.
Thanks everybody for your time. Thanks for having me, and hope to talk to some of you soon.